Okay, so I would like to start today again with giving you space for questions and discussion. Do you have any topic you want to revise? So is it okay we proceed with the new things? I mean, what I have for today is the section on algebraic closure and possibly a few other things. So
Yeah, I think we can give it a go.
yeah, okay. So let's nevertheless do a recap. Um, uh, I mean, we have for any prime power, I will write it Q. Q is p to the n for some n. There exists a field FQ with a number of elements of FQ is Q, p to the n. Of course, this FQ must have a characteristic P. So any field of characteristic P contains let's call it a copy of FP. Right? I mean, you take 1 plus 1, and so on, and you get something isomorphic to FP. Yes.
Yeah, sorry, Matan. So I remember that the characteristic of a field is, as you said, the amount of times you can plus one your identity until you get back to zero.
Yeah.
But how like how is this relating Q and P here? Like,
so Q is a power of P, right? Remember that I mean a field can only have a characteristic P for some prime P.
sure, yeah. So Q is
Okay,
like an extension.
and of course FQ with addition and 0 is an abelian group. This means that the order of any element x in FQ must divide by Lagrange. It must divide p to the. I mean, it must divide Q, which is p to the n. Right? For any x.
Yep.
Many x in FQ. So it means that x plus x, at some point it becomes 0, right? It cannot be otherwise. And the minimal, I mean, so the order of x, it must be p to the k for some k, for some k smaller than n, right?
Yeah.
And so since we know, so it cannot be any, so the of course this kind of expression is simply can simply be written as 1 plus 1 times x,
Yeah. Agree.
right? And if this is equal to 0, right, that's what it means, that the order of I mean,
Yeah.
let's say this is p to the k, then it means that 1 plus 1, since x is not 0, it means that 1 plus 1 plus 1 p to the k times must be equal to 0, because in a field you cannot have, you don't have 0 divisors. I mean, if two elements multiply into 0, one of them must be 0.
Yeah.
Okay, so okay, so now this means that the characteristic of FQ must be P, in fact, because it cannot be for any other prime. You will not have 1 plus 1 plus 1 equals 0.
Agree. And that is, does that have something to do with the fact that Q, I don't know if that's correct to see it on that way, but it's an extension field based on P?
Yeah, that's another way to see it. It is, I described kind of elementary view, but FQ is also a splitting field, alternatively. FQ is a splitting field of the polynomial x to the p to the n minus x over fp. So splitting field is an extension of
Yeah, I see.
so it must have characteristic p.
Thank you very much, man.
And moreover, what we saw, it's essentially because of the uniqueness of splitting fields up to isomorphism. So up to isomorphism of fields, any field f with q to the I mean p to the n elements as isomorphism of fields between f and fq. Okay, so in this kind of situation, I mean, you could define FQ in various ways. I mean, even when I say FQ is a splitting field of this polynomial, again, splitting field is not unique on the nose. It's unique up to isomorphism. So to be kind of administratively clear, we choose one construction for FQ. One possible way is we defined explicitly how to do a splitting field, how to construct a splitting field from a given polynomial, and for us this would be the definition of FQ. But of course you could do it differently, and you will get something isomorphic. So just to kind of disambiguate what we mean, I mean, FQ is a specific construction, and possibly, of course, many situations can give rise to other fields of P to the n elements, but they will be isomorphics. If you think of it, it's a bit like I mean, we define the FP as integers modulo P. I mean, 0 up to P minus 1. With addition and multiplication modulo P, but we didn't have to do it. I mean, we could also do, we could also take the integers modulo the subgroup generated by all multiples of P. And this is isomorphic to ZP. So I could define FP to be Z modulo PZ. And it is isomorphic, but again, to be kind of clear on what we mean in the point set level, we fix one construction as the one we call FP. Okay, so what we want to do now, after classifying all finite fields, is to classify all finite field extensions. So this is just a terminological issue. We say that for subfield inclusion, let's say F in K, we say that K is an extension of F. Okay, so it's kind of two points of view. Either F is a subfield of K, or K is an extension of F. And what we want, after classifying all finite fields, is to classify all finite field extensions that means given a finite field let's say FQ, what are the possible finite, well, subfields F inside FQ? Okay, so and this will help us in what we construct. Of course, one quick answer is that FP must be a subfield of FQ. So at least we have one subfield of FQ. To get a bit better view, let's have the following lemma. I claim. Is there a question?
Yeah. When you classify all samplings, do you mean by classify somehow describe all possible, in our case, field extensions?
Yeah, classify is kind of a soft notion. It's a soft statement. It's not like a rigid mathematical claim, like we have in the statements of lemmas, propositions, and theorem. But what it usually means is to have a condensed or a short description or neat description of all possible objects of a given type.
Okay, thank you.
Okay, so and this is a recurring theme of we had, because we talked about classification of abelian groups, finite abelian groups. A finite abelian group is originally defined abstractly, right, as like something with a binary operation satisfying some axioms. And the classification of finite fields, of finite abelian groups was, in fact, every finite abelian group is a direct sum of cyclic groups. So this is considered the classification because it's a neat description of all objects of a given type. And the same goes for finite fields. Okay, so the following lemma is going to be useful. It's a kind of a number theoretic statement. If P is a prime, I claim that a P to the M minus 1 divides P to the N minus 1 if and only if M divides N. The way to go about it is there is a famous identity for any x is kind of a polynomial identity. I can write x to the n minus 1 as x minus 1 times x to the n minus 1 plus plus this term. And I mean, the way to see it, you get, I mean, things cancel out. I mean, you do x times this, you get x to the n. Then you multiply, then you get a bunch of other stuff like x to the n minus 1 up to x times 1, which is x. But then you do 1 times x to the, I mean, minus 1 times x to the n minus 1. So you get minus x to the n minus 1. And you continue doing, you basically cancel out all the expressions minus x, but then the last expression does not cancel out. The last expression is minus 1 times 1, which is minus 1. Okay, so this is indeed x to the n minus 1. Okay, let me just I can write it like this. X to the n minus 1 is x minus 1 times the rest of it. And this is the key fact for the proof of the lemma. And now, how do we proceed? So we have an if and only if here. Let's do one direction. If m divides n, so let's say n is equal to m times k. Then I write p to the n minus 1 as p to the m to the k minus 1. And now taking in this identity x equals p to the m, what I get is like p to the m minus 1 times p to the m, or let me write it shortly as sum p to the m to the j, where j is from 0 to k minus 1. Yes?
If you did the substitution of x equals p to the m, but you kept writing everything with p to the m, is that intended, or?
Yeah, no, I didn't do the substitution. I just, I mean, I'm just saying I'm using this box star.
Yeah, fair enough. Fair enough. Okay, I see.
Okay.
I see. Thank you.
And from this, it follows, of course, that p to the m minus 1 divides p to the n minus 1. Conversely, if p to the m minus 1 divides p to the n minus 1, and I write n equals, let's say, mq plus r. I mean, I do long division of n by m. Then of course, this R is smaller than M and bigger or equal to 0. And what I can write, I mean, p to the n minus 1 divided by p to the n minus 1. This is, we assume to be an integer. But it is also equal to p to the mq plus r minus 1. Or let me write it slightly differently. Here I have p to the m minus 1 and p to the mq plus r minus p to the mq plus p to the mq minus 1. And now I just split it. So this is p to the mq plus r minus p to the mq divided by p to the m minus 1 plus p to the mq minus 1 divided by p to the m minus 1. Yeah, so let me call this this thing t. Of course, t must be equal to, I mean, t must be an integer. Sorry, actually, we write it as p to the mq p to the r minus 1 divided by p to the m minus 1 plus t. Now, t is in z, t is an integer because we already proved that, I mean, since m divides m times q, we know that p to the m q minus 1 is divisible by p to the m minus 1. This is the first part of this lemma. If t is in z, it means that p to the mq times p to the r minus 1 divided by p to the m minus 1 is also in z. Right? Because the initial expression was an integer. And this means that p to the m minus 1 divides p to the r minus 1. But I mean, r is smaller than m, right? R was the remainder of doing a long division of n by m. So we must have r equals 0. And this means, of course, that m divides n. Any question about the lemma?
I
Yes.
have a question. So in this last step, how do you get that r is 0? Like, okay, it must be smaller than m, but why 0? And I mean, I deduce that this means that m is 1, but I'm not sure.
I mean, if m is bigger than r, then p to the m minus 1 is bigger than p to the r minus 1.
Yes, so it's clear that R must be smaller than M. But what I don't see is why this leads to R being like 0.
Because, I mean, how can a bigger number divide a smaller number? The only way, I mean, the only way that a bigger number can divide a smaller number
Wait.
is
Sorry.
if the smaller number is 0. I mean, then, okay, everything can divide 0.
Okay. I'm sorry. Thank you very much.
Yes.
Can you explain a bit again these manipulations with powers that help us to understand that something is an integer?
You mean this part?
I think they are very similar. That's why, like any part, for example, like but the second when you say that like now t is in z.
Yeah, I claim that. Okay, so I claim that t is an integer because m divides m times q. I mean, we had the first part of the claim was that if m divides n, if m divides n, then we have this purple division relation.
Yeah, right.
Okay, so I mean, I use it when I claim that t is in z. I mean, m divides m times q. So p to the m minus 1 must divide p to the mq minus 1. It's like you put, you can call this guy n. Or
Is it like a rule? Like I understand that like m divides mq, but I don't understand why p to the power mq minus 1 will divide.
will be divisible. Yeah.
Yes.
I mean, this is the first part of the claim. If you have two integers, m and n, or
Yes. Okay. I understand.
okay.
Yes.
So yeah, so t is in z, and since t is in z, then this guy must be in z, right? Because the whole, I mean, we started by the assumption that p to the n minus 1 divided by p to the m minus 1, this guy is in z, is an integer. So if t is an integer, is this clear? You have any other doubts?
No. Okay. It's okay now.
Okay. One thing I didn't say is that I mean, why do I mean, why does it have to be, if this is an integer, why does it have to be that p to the m minus 1 divides p to the r minus 1? I mean, couldn't it maybe it cancels out with p to the m minus k? Sorry, with the p to the mq. But the GCD of PMQ and p to the m minus 1 is 1. I mean, they are not divisible by, I mean, they don't even have a common factor, right? Clearly, I mean, if you do long division, you get something non-zero. I mean, you get a so okay, this is a kind of a technical issue, but it's going to be useful for us later or soon. And this is the following theorem. let Q be a prime power. And then for every M that divides N, there is a unique subfield F of FQ with exactly P to the M elements. And moreover, every subfield of FQ is obtained is of this form. Is of this form. Okay, so this you can regard this statement is like the classification of finite extensions. Is the statement clear? It's a bit long, so yes.
So to summarize, what you're trying to say here is for every root of M, so for every divisor of M that we can find that doesn't give us a residue also, we can derive from there a subfield for which the original field can be seen as an extension field of.
Exactly.
Okay.
So what the statement tells us is, I mean, you can view it this way. I start with FP. Then I could extend it to FP square, for example. And I could also extend it immediately to FP cube. But I don't have an inclusion here because 2 does not divide 3.
Yep.
However, I could go for FP to the 6. And FP to the 6 does include FP to the 3 because 3 divides 6. And it also includes, I mean, FP to the 2 because 2 divides 6. So, yes.
Yeah, sorry, but now that you're saying that, it also made me wonder if we are extending fields, what's happening with the primitive polynomials over which the field lays on? Like,
I mean, the prime polynomials, the notion of a prime polynomial is intimately related to the field in which it is defined over. So I could have a polynomial here, fx, which is prime, but here it may not be prime, right?
exactly.
Okay, and once it is not prime, I mean, if it completely splits, I mean, if f splits here, then
But
it also splits in any extension, because
but it's a bit unfair because you can always split, right? Like you can always find a splitting field. You might need to go to the complex numbers or whatever, but you can always split it somehow.
yeah,
So it
but
just never ends.
yeah, I can eventually I can always split, but I mean I don't know that necessarily it splits in FP square. What could happen, and what typically happen, is that you extend you are after one extension, let's say this one. After one extension, you find one root or two roots, but it doesn't completely split. So you need to go further to another extension.
Okay.
And then you get more roots, and you continue until you get all the roots.
Okay. And
That's basically how we constructed the splitting field, right?
Sure.
We did it in stages.
mhm.
Okay, but what I want you to remember from this this picture, the splitting issue is not the main thing, but rather that we don't have a subfield inclusion or a field extension in this case, in this purple case. Yes.
Yes, sorry, Matan, I don't want to stay here forever, but I have another question.
Yeah.
So far, we are proving this inclusion or non-inclusion basically by division without remainder, so exact division. But depending on the on the primitive polynomial that FP2 and FP3 are defined over, these fields indeed could be like could have this inclusion, no?
Okay, so
Is it true?
It's true. So this is important. When I write here included, I mean not included here, it doesn't mean they are not. They could be there could be an inclusion of sets. For example, FP in our definition is just the numbers 0 up to P minus 1. So you could say it is included as a set. It is included in the real numbers, right? The real numbers contain 0 up to P minus 1. But this is not a subfield inclusion.
Okay, I see. Fair enough.
And that's the important. It's really crucial. We care the most about. I mean, we essentially only care about subfield inclusions because the fact that the two sets are included is not very helpful if the operations are different.
Yeah, exactly.
Okay, so depending on our definition, on our kind of point set construction, it could be that FP square is included in FP, but they will not be, according to this theorem, they will not be subfields. I mean, or a field extension.
Okay, thank you. So, thank you very much.
Okay, so let's prove the theorem. Suppose M divides N. We showed that the multiplicative group FQ star, it means you take FQ, you remove the zero element, and you look at it as an abelian group with respect to multiplication. And we showed that this group is I mean, actually, there is nothing to show. This is a group is of order q minus 1, which is p to the n minus 1. And by lemma, p to the m minus 1 must divide p to the n minus 1. Now, if you recall, this was a corollary of the classification of finite abelian groups. We had what we called converse Lagrange theorem. It means that if you have an abelian group and you have some number dividing the order of this group, then you must have a subgroup of this order. So by the converse Lagrange theorem, there exists a subgroup which I will call K star. And this is a subgroup of FQ star of order p to the n minus 1. And now define K to be this K star union the zero element of FQ. So of course, K by definition, I mean K star by definition has a multiplication. But in fact, it also has addition. It has addition because we can induce the addition from, it is a subset of FQ. So we can use the addition of FQ to add two elements in K. We will observe that we can restrict addition and multiplication in FQ to K. The question is, so K has it has a zero element, right? This by definition. It has an element 1 because it is a multiplicative subgroup of FQ star. And we can add two elements and we can multiply two elements. If I multiply two elements in K, I mean in K star, for example, then I know I get a new element in K star. This is because K star was chosen to be a subgroup. But I still need to justify why, if I add two elements in K, using the addition coming from FQ, why do I still get an element in K? So if A and B are two elements in K, well, let's view it this way. So this, we use Lagrange, converse Lagrange, but we can use Lagrange theorem. Every element in K star satisfies x to the p to the, what is it, m minus 1 equals 1, right? Because the order of the group K star is p to the m minus 1. So, of course, the order of every element must divide p to the m minus 1. If I raise the element to the p to the m, the order of the group, I must get 1. But of course, this is equivalent to say that for any x in K, x to the p to the m minus x is equal to 0. This was for any x in K star, but if I do it for 0, that's I mean, that's trivial. What this means is, okay, and now I take two elements in K. Then if I do A plus B, and I raise it to the p to the m, then by the freshman exponentiation, this is a to the p to the m plus b to the p to the m. But by this identity star, since a and b are in K, I get that this is a plus b. So a plus b is a root of x to the p to the m minus x. And this means that a plus b is again in K, because K has exactly p to the m elements, and therefore all the roots of this polynomial, I mean all the elements of K must be precisely the roots of this polynomial. And this polynomial has p to the m roots. So if I know that a plus b is a root of this polynomial, I get that a plus b is an element in K. This means that K is closed under addition. Of course, it's closed under multiplication, and you can show, maybe it's good. It's a good exercise. K is also closed under additive and multiplicative inverses. Yes, a question?
Yes, I'm sorry, I missed like I think I'm not sure about the last step. So I understand why a plus b to the power of pm equals a plus b, but then the conclusion of a plus b is a root of x to the p to the power to m minus x. I'm not sure I see it, and why is it then a field, an element in K? Like the last two steps, I'm not sure I really understand them. Could you go through
Okay.
it?
Yeah. So the second to last step is fairly easy. I mean, if something is a root, if something is a root of x to the p to the m minus, x is a root of, or let's call it maybe t. T is a root of x to the p to the m minus x, if and only if t to the p to the m is equal to t. So if I prove that a plus b to the p to the m is equal to a plus b, it means that it's a root.
Makes sense.
Okay. Now I claim the number of elements in K is exactly p to the m, right? I mean, we started with a subgroup, a multiplicative subgroup of size p to the m minus 1, and we added 0. So
Right.
we have p to the m. All the elements of K satisfy are roots of this polynomial, right? Because all the elements in K satisfy by Lagrange, all the elements in K satisfy x to the p to the m minus 1 equals 1.
Okay. I guess I'm not sure I follow the step from this one to the x to the p to m minus x equals 0, the star.
Well, just multiply by x.
Okay, right. It does work here.
Okay, so I know for any element in K star satisfy
Makes sense.
x to the p to the m minus 1 equals 1.
Yep. Makes sense then.
And now it means that every element in K satisfy x to the p to the m minus x equals 0.
Yes.
So all the elements in K are roots of the polynomial x to the pm minus x. But this polynomial can have at most p to the m roots. So it means that all of the roots of these polynomials are the polynomial are in one-to-one correspondence with the elements in K.
Makes sense now. Okay.
And now I take some pair of elements a and b in K, and I add them together. I find that a plus b is again a root. It means that a plus b is in K.
Perfect. Thank you. Makes sense.
Okay, so as an exercise, you can prove that if I take minus a, for example, if a is in K, then minus a is in K. I mean, a is in K. I claim that minus a is in K, and also if a is not 0, then a minus 1 is in K. I mean, this part actually you don't need to show because K star was a multiplicative subgroup, so it contains all the multiplicative inverses. The way to show that you have an additive inverse, I mean that additive inverses are also in K is, I mean, the additive inverse would also be a root of this polynomial. Okay, so it must be in K. And this is all to say, so to sum up, we have a subset of F, which is a field. So this is a subfield. Of size p to the m. Okay, so this, but of course, this relies on the fact that m divides n. So now we turn to uniqueness. So if F is a subfield, I mean, the claim of the theorem, I remind you, is that there is only one, I mean, for every m dividing n, there is exactly one subfield of FQ of size p to the m, and no more. I mean, so to show this second part of the claim, I mean, the uniqueness, let's suppose I have a subfield. Then clearly by Lagrange, the order of f, I mean, f is in particular an abelian group under addition. And if it's a subfield of FQ, in particular, it will be a subgroup of the additive group of FQ. So it means that the order of F must divide the order of FQ, which is P to the N. But of course, the order of F is some power of P, let's say P to the M, for some N, or some M. Yeah. Now, the multiplicative group of F is a cyclic of order P to the M minus 1. Actually, the cyclic is not necessary. So its elements are precisely the roots of x to the pm p to the m minus x. Or actually, since we're talking about f star, I guess we could say it like this. So so the elements of f are precisely the roots of the polynomial x to the pm minus x. And well, I mean, over FQ. And this defines uniquely the set F. Thus, F is unique. Sorry. Is this clear? This completes. It was a bit cumbersome way, but is this issue okay? Hello?
I think I put hands up and no one said anything, so I think it's clear.
Okay, so let me just quickly revise and we can then take a break. I mean, basically, what you see is that the only way to get a subfield of FQ is to have something of size p to the m where m divides n. This is because of the lemma. I mean, it's because of the lemma tells you that p to the m minus 1 divides p to the n minus 1 if and only if m divides n. So by kind of Lagrange argument, that's the only way you get a subfield. And then you see that any such subfield must be the roots of the polynomial x to the p to the m minus x, and this essentially pins down the only option you get. I mean, it means that there is a unique subfield of this form. Okay, and then so this picture here is the way to view it. Let's take a 10 minutes break, and we come back to define the algebraic closure and the defining property. Can we start again?
Yep.
Okay, so what we have from the classification of finite field extensions is we can construct a tower starting from FP, going, well, if I do FP square, I could do FP square, but then I do not have a field inclusion into FP cube. So instead, what I'm going to do is, I mean, I do FP square, and it is included in FP 3 factorial. So I regard it like this. Of course, I mean, n minus 1 factorial always divides n factorial. So I have this tower, and this can go to infinity, right? And in fact, I don't have to start with FP. This is FP. I could also start with FQ, and I know that FQ is contained as a subfield in FQ square. Of course, Q here is, as usual, a power of P, and FQ square is going to be included in FQ 3 factorial. And so on, up to infinity. So what I'm going to do, I mean, the algebraic closure of FQ is simply you take the union over all these, I mean, of all this tower, this is fq to the n factorial, where n is an integer, so is a natural number. So maybe n goes from 1 to infinity. And the important property of the algebraic closure, so of course the algebraic closure is no longer a finite field, but nevertheless it's very useful for us in studying finite fields. Well, first, in proposition, I claim that fq bar is a field. The way to see it is yeah.
Sorry, I'm a bit confused by the definition of the algebraic closure, because if you start by, for example, if you put n equal 1, the first, so you have fq to the factorial of 1, and then you adjoin fq to the factorial of 2, but we know that fq to the factorial of 1 is already included in fq to the factorial of 2. So like you don't add new stuff, because only the last, I mean, it's not the last because it's infinity, but only the last step will, each time you increase, then you already contain the previous field that you defined before.
Yeah, that's exactly, I mean, that's exactly the reason I need to take it, I need to take the infinite union, because in any finite piece, okay, let me just maybe stay where we're heading. What I'm going to prove is first that this algebraic closure is a field, and second, that every polynomial splits over the algebraic closure. So, and of course, you cannot expect that if I give you a polynomial of degree d, and if d is bigger than n, or if d is bigger than n factorial, or if d is bigger than q to the n factorial, then f cannot possibly split over f q to the n factorial, right? Because there is only a q to the n factorial elements, and the degree of f is bigger than that. So it cannot have all the roots in fq to the n factorial. So what happens is that if I want kind of a unifying framework in which every polynomial splits, then I need to go up to, in the ladder, up to infinity. I mean, I kind of push my problem to infinity, and then it gets solved. So that's the reason I need to take the infinite union. Now, of course, you could say, okay, I mean, if you're only interested in f to the q3 factorial, you shouldn't care about this and about, I mean, about the previous pieces. But what I really care about is not any of the finite pieces, but rather the union of all of them. Is this answering your question?
Yeah, kind of. At least I see the why we need to go to infinity to have this for any polynomial. Yeah, makes sense.
Yeah. So okay, but I will prove it. It's not. I mean, it's not yet rigorously shown. Okay, so let's first prove that the algebraic closure is a field. So first, FP is contained in the algebraic closure. It is contained in f q to the n factorial for any n. And this means that it is contained in the infinite union. This is a subfield, of course. And it means that it is contained in the union, which we define to be the algebraic closure. For now, we only have, I mean, we only know that it's a set inclusion. We cannot possibly say that it's a subfield inclusion because we didn't prove that FQ bar is a field. That's really the claim. But in particular, so we set the zero element in FQ bar and the unit element in FQ bar to be those of FP. 0 FP, 1 FP. Now, how do I define addition and multiplication in FQ bar? To define addition and multiplication, let x and y be two elements in FQ bar. If an element, I mean, if I have an element in the union, it must belong to some finite piece, right? I mean, then there exist n and k, let's say, such that x belongs to f q to the n factorial, and y belongs to f to the q k factorial. Now, I don't know, maybe n is bigger than k, maybe k is bigger than n. I don't care, because these guys must be subfields of f to the q to the n factorial k factorial. So it means that x and y are elements in this bigger field. And in this bigger field, I can multiply and add x and y. I mean, possibly, I don't know how to add x and y if I think of them as elements in these fields, because it could be that n does not divide k, and also k does not divide n. So if x and y do not live in the same place, I extend it enough so that they will live in the same field, and then I can add and multiply them. And so addition and multiplication is defined in this way. Clearly, if x is an element in FQ, let's say x belong to the piece FQ to the n factorial, then x minus 1 and also minus x would also have to belong to the same field, f q to the n factorial. Hence, they belong to the algebraic closure. Okay, so this basically now associativity, all the axioms say associativity, commutativity, and distributivity. Of the plus and multiplication in FQ bar follow from the corresponding axioms in each of the finite pieces. Okay, so what I conclude is that FQ bar, again, the union of f q to the n factorial, is a field. Is this proposition clear? Yes.
So it makes complete sense to me. I'm just wondering, doesn't having a characteristic of a field being infinite cause any kind of problems or trouble when formalizing FQ of n? I'll say it someday. Factorial.
Say that again, Carlos. I couldn't hear.
Yes. So what I meant is, if you have you're basically saying that FQ of n factorial has an infinite characteristic for the field.
No. That's
How is that? How it doesn't have an infinite order? Or an infinite
it has an infinite order, but not infinite characteristic. Recall that a characteristic of f is the minimal number.
Oh, you're right. It's okay. I see. You're right. You're right.
Such that 1 plus 1 plus 1 equals 0. If this minimal number exists. Of course, if it doesn't, then the characteristic is 0. So any field containing, since FQ bar contains FP, it means that FQ bar is of characteristic P. This, you have no choice. Because but it is of infinite order. It's kind of it's a new phenomena for us, a field of finite characteristic, but of infinite order.
Okay, but since it follows the axioms, it doesn't prevent us from saying that it can actually apply all of the corresponding operations, although it has an infinite order. Hence, we don't know the modulo that we're applying.
I mean, in all our development of the basic theory of fields, we never restricted the definitions to include only finite fields. I mean, and indeed, we talked about the real numbers, the rationals, and so on. So a field does not need to be finite. It's a new phenomena. I mean, until now, the only positive characteristic fields that we saw were finite. But in fact, this new construction gives us an infinite field of positive characteristics.
Understood. Thank you.
maybe I can add that if a field is of characteristic 0, then it is automatically infinite, because it has to contain 1, 1 plus 1, 1 plus 1 plus 1, and so on, and all of them cannot be equal to 0. So they are all different, because I mean, if 1 plus 1 would equal to 1, then it means that 1 is equal to 0, and so on. Yes.
So just I want to make sure I understood, because what you just wrote, like the fact that I think it's a thing that you already saw before, but the fact that the characteristic of f, so sorry, the characteristic of the algebraic closure is the same as the characteristic of FP, is because the one you define is the one from FP. But you could really define a one from from another extension field. Like you could define a new one, right?
I could. I mean, to be more precise, it's because I defined the one in FQ bar to be this is here in the blue box.
Exactly.
But I also defined the operation to be the operation induced from any of the finite pieces. Any of the finite pieces contains FP as a subfield. So it means that if you do addition of the element 1 in any of the finite pieces, it's like doing addition of the element 1 in FP. You see my point?
Yeah. Yes. Because my next question was related to this, like why can't you choose another definition of 1 in the algebraic closure? You could define the 0 FP on FP, like 0 FP square and 1 FP square, for example.
Yes, but because they all contain FP as a subfield, the 0 and 1 in these extensions must be the original 0 and 1 in FP.
So you cannot define 0 and 1 in from FP square, for example. You have to choose the same 0 and 1 that are the one from FP.
No, I don't have to. I mean, okay. What I'm saying is you could choose a 0 FQ bar to be a 0 FQ.
Yeah.
Okay, for
Exactly.
example.
Yeah.
But what is 0 FQ? FQ contains the subfield FP.
Yeah.
What does it mean that it contains it as a subfield? It means that the 0, 1 in FP are the same as the 0, 1 in FQ.
Okay, that's the definition of what we call a subfield then. That's
Yes.
okay.
A subfield, it's like a subgroup. A subgroup must contain the unit element of the original, the neutral element of the original group.
Perfect, thank you.
Okay. So in fact, here I basically had no choice but defining the elements. I mean, the 0 and 1 elements as the one coming from FP.
Yeah, I see that now. Okay, thanks a lot.
Okay, so this is the. Are there any other questions? This is the algebraic closure. It's a field, and now I claim that we have kind of a perfect setup in the algebraic closure in the sense of the following theorem. Let Q be a prime power. And I take some polynomial, I don't care what is it, in polynomials over the algebraic closure. Right? We just proved that the algebraic closure is a field. So I can take a polynomial over this this field. Then F splits to linear factors let's say F is equal to alpha times the product of x minus alpha I equals 1 to n. Of course, for alpha and alpha 1 up to alpha n, some elements in the algebraic closure. Okay, so how do I prove it? What the kind of line of argument that we do in algebraic closure is we move to a finite setup if we can. And what happens in a polynomial, I mean, f has finitely many coefficients. Let's say A0, A1 up to AN. Each of the AI, it is in the algebraic closure. So each of them separately must belong to some finite piece. I mean, this the algebraic closure is a union of finite pieces. So all of them together must belong to some finite piece. So there exists, let's call it capital N, such that A0, A1 up to AN belong to F Q to the N factorial. i.e., I can write F or Fx as a polynomial over Fq to the N factorial. Okay. So now I can do, yes?
Can you give a bit more intuition about writing f of x within fq of n factorial again? I'm not sure I follow, like, why is this relevant, or what is it like kind of proving?
I mean, what I want, okay, let me just, what I want to do now here is, I mean, I will construct a splitting field of F. The splitting field of F, a splitting field of F is F, I mean, it is F to the Q N factorial times, I don't know, D for some D. But this splitting field is, of course, is contained in just another finite piece. Let's call it F to the Q N prime factorial. And this guy, of course, is contained in the algebraic closure. This means, so I mean, of course, if a polynomial already splits in a subfield, then it splits in the extended field, right? I mean, so f splits in f q to the n prime factorial, hence also in f q bar. Okay, so this, let me just repeat kind of the line of argument. We know that, I mean, we constructed splitting fields over finite fields. So if I am given a polynomial over the algebraic closure, the way to see that it must split in the algebraic closure is first to go back to the finite case. The way to go back to the finite case is that a polynomial is a finite creature. It's like it has finitely many coefficients. If it, I mean, because of this, it means that it must belong, even though the coefficients are officially in the algebraic closure, all of them must belong to some finite stage of the tower. And if they are in a finite stage of the tower, they all belong to some finite field. And I can construct the splitting field over this finite field, which will again be just another finite field, hence contained in some other finite piece of the tower. And once I know that the polynomial is splits over a subfield, it must split over the bigger field. Any questions about this this proposition? This is really like central to what we will do later. Yeah.
Yeah, I didn't follow exactly like the proof itself, I would say, to be honest. Could you give like the intuition from maybe not a different perspective, but phrase it on a different way?
Let me try to repeat with like maybe slight modifications. Sure. Look, the statement is that every polynomial over the algebraic closure splits to linear factors. I mean, splits to linear factors is the same. I mean, for us, splits means to decompose into linear factors. Now, in particular, if you look at the statement, of course, if you have a polynomial over fp, then in particular, it will be a polynomial over fp bar, right? Because fp is a subfield of fp bar. If I have a polynomial over a small field, I can think of it as a polynomial over a big field. But I can also do, but in the case of fq bar, I can also go in the other direction. How do I go in the other direction? F has finitely many coefficients. I mean, let's say f is equal to sum ai x to the I. Right?
Yeah, sure.
And all of the coefficients a0 up to an, they, I mean, by definition, they are elements in the big field fq bar.
Yeah, exactly.
But what is FQ bar? FQ bar is the union of all FQ to the n factorial n equals 1 up to infinity. If A0 is an element in FQ bar, then it means that there is some n, let's call it n0, such that A0 belongs to FQ to the n0 factorial. You see this?
Yeah. Until now, I follow.
Okay, and the same goes for the rest of the coefficients. I mean, all of them will belong to some finite stage of the tower.
Sure, yeah.
But once all of them belong to some finite stage, I can take, I mean,
Oh, I see. So once all of them are in a particular, let's say, floor of the tower, you can get the maximum floor, which will be finite and not infinite
Exactly.
anymore. Okay.
So,
I'm so stupid. Yeah, thank you.
there will be some n. I mean, basically, you could take n to be, you could take n to be the product of all the ni's. I equals, well, I mean, you take all the product of all of them, and you get some kind of I mean, some stage of the tower for which all of the coefficients of the polynomial f are in this stage.
Makes sense.
Okay, but if all the coefficients of f are in this stage, I can think of f as a polynomial over this subfield. I mean, this guy is a subfield. FQ to the n factorial is a subfield of FQ bar.
Sure, yeah.
Okay, so I can think of f as a polynomial over the subfield. Now this subfield, it's a finite field. So I can do the splitting. I have a splitting field.
Yeah, correct.
The splitting field is of a polynomial over a finite field is again a finite field.
Yeah, sure, yeah.
Right? And so it must be contained in some stage of the tower.
Oh, okay. I see now. I see. That makes
Yeah,
sense.
because the tower,
Yeah.
remember the tower, let's say I start with FQ, then I do FQ to the n factorial, sorry, FQ 2 factorial, and so on. Here I have FQ to the n factorial. If you give me a finite field of the form FQ to the D, of course it is a subfield of FQ to the D factorial. So it is always, any finite field is contained in some stage of this tower.
Sure, that makes sense.
Including the splitting field of F. So the splitting field of F is contained in some stage of the tower, and hence F must split over the algebraic closure.
Okay. Okay. So the only thing that now I'm missing, but I guess we will see it later, is how this is useful for us in later stages, like that we are able to prove this exact thing, because it looks really abstract to put it on some sense.
Yeah, it is abstract, but you can think of it as kind of a unifying framework for polynomials. I mean, of course, I mean, for let's say I even only care about polynomials over FP, but they don't have, not all the polynomials over FP have roots in FP.
Okay, fair enough.
And So of course, if I take one particular polynomial, if you told me in advance what is the polynomial you're interested in, I can take a splitting field of this polynomial. It will be some finite field, and I can look at these polynomials over the splitting field. And then it will be good for one particular polynomial that you chose in advance. But if I don't tell you anything in advance, and I want a framework so that every polynomial you throw at me will split, then I need to push these constructions of a splitting field to infinity.
Yeah, that makes sense. That makes sense.
Okay, and what it does for you is it unifies the statements you want to make about polynomials without without choosing in advance a particular polynomial.
Fair enough. That makes complete sense. Thank you, Matan.
Okay, so other questions about the algebraic closure? Let me finish the session with the what is called the fundamental theorem of algebra. And this says that every polynomial over the complex numbers splits to linear factors. Okay, so this is this we don't prove, but it. And I didn't define the algebraic closure of a general field, but what's happening here is there is a wider definition of algebraic closure, even more abstract than what we did, that is applicable to any field. And if you take the algebraic closure of the real numbers, you get the complex numbers. Okay, and an even more interesting thing would be to look at the algebraic closure of the rational numbers. The algebraic closure of the rational numbers would contain the rationals, but and it will be contained in the complex numbers, but it's not equal to the complex numbers. So there is a lot. I mean, understanding the algebraic closure of the rational numbers is like a modern research topic. So that's kind of the slightly wider picture. Yeah. All right. Yes, Carlos?
Are there any resources like that are feasible or accessible to read about the fundamental theorem of algebra?
About what?
About what you just explained.
Yes, I don't have something off the top of my head.
Because we will not see it, right?
Yeah, we will not see it because we don't need it.
Yeah,
we only need the algebraic closure of finite fields.
Makes sense.
We could potentially use. I'm not sure we even use the fundamental theorem of algebra. But it is useful to know. I mean, it tells you that once you add the root of the polynomial x squared plus 1, you kind of automatically add all the roots to all the polynomials. So that's
Cool.
It's a nice property.
Okay, thank you. Thank you, Matan.
All right. Next time, of course, you can always come up with questions on previous material. But I have something prepared for next time. This is well, equivalence relations and maybe the projective space.
Cool. Awesome.
Okay, so have a good day.
Cheers.
Thank you. Bye.
Bye.
Thank you.